Record. Okay, now we're recording. Sick. All right, sharing my screen. My screen is the second screen. VHDL, the deliverables board. That's right. Okay. All right. Here we go. Operate. Yes. Operations, retired operations, enduring education, learning, materials. Here we go. Oh, here it is. All right. Introduction to materials. Right. So, this is stuff that I made for my high school game dev club right back in the day. But just gonna talk a little bit about what materials are. So, in a game engine, you have to describe what the computer is going to do when it hits a surface. When a pixel, like, you know, your screen is like a billion pixels, right? And when one of those intersects with the surface of like a cube or a water bottle, it's gonna go like, hey, you know, is it transparent? Is it like, am I going through the bottle? You know, am I going to like bounce off the surface? Is there reflections happening? Does the surface what does the surface look like? You know, what color is it? And that is defined by a number of properties that overall describe the shading of the surface. That's what we call that. This applies to any game engine. This isn't like just Unreal Engine stuff. Hell, it's not even just Unreal or Unity stuff. This applies to Blender. It applies to any renderer. Anything that's rendering something, that's taking like a set of 3D objects and creating like a final image, is probably utilizing shaders unless it's very, very rudimentary. And even then, like, just a basic texture applied to a surface could be considered a shader. Like, a texture is the 2D image, like a brick pattern, and then a shader describes how that texture is applied to the surface. So maybe positioning, maybe the lighting of that surface in addition to just the solid color. So, and Unreal compiles every single one. Yeah, so, okay, cool. Right, so, let's talk a little bit about shaders. This is what the node editor looks like in Unreal Engine for shaders. This is like the Unreal Engine interface here. So what exactly is going on here? There's like a preview area. There's like the node editor area, like the main area. This palette on the right, I don't think it shows up anymore by default. But if it does, it's not that important. Same with the statistics thing. But this is where you edit materials. Now there's some vocabulary here. You know what? Let's roll back the clock a second. Objects have material IDs. In one of the first beginner sessions, we discussed those. I'm just going to do a quick review for those of you that maybe missed it or weren't here. Don't care about that, and that's fine. You got to understand that an object, here's like a cube in Blender, right? I'll add some details to it. Just there. There. This object here has a bunch of faces. Each of these faces has a material ID. So over here we can like describe what materials go on what face. So this material, we'll make another material. We'll call this material 2. I can say, hey, material 2 is green and assign it to that face. And we don't see it here, but we see it there. And I can assign it to this face and this face. And then material 3 might be like just red. And maybe I assign it to this face. And maybe I can say material 3 is also really like metallic and shiny. And, you know, so you can describe the shading of a surface with materials. This is in Blender. We're not going to focus on Blender because Blender, depending on the rendering engine that you're using, which is either like one that uses photons or one that works like Unreal Engine, it's a little different. It uses different like shading systems. But don't worry about that. The point is, every face in an object has a material ID that says, hey, all of those faces, the orange ones right now, are associated with the first material slot. All of the green faces are associated with the second material slot. And so when I grab this and I bring it over to Unreal Engine, it will have slots. And in those slots, material 1, 2, 3, etc. You put the shader, the material. I'm using these a bit interchangeably, these words, material and shader, because they are used a bit interchangeably in the industry. In Unity, you create, I believe, a shader graph, and then from the shader graph, you create materials. In Unreal Engine, you create a material, and from the material, you create material instances. But a material is a shader, and a shader is a shader, and those instances are instances in either case. So it's, the vocabulary is weird. I'll explain what all of this means in a little bit. I promise. I absolutely promise. I know that's kind of weird. William might, one thing that helps with shaders is understanding how you can layer different images together to create different effects. We'll talk about that. We'll talk about all of that. That's William talking in muted mics. So before we move on, let's talk a little bit about the outputs. So in Unreal Engine, these are the outputs to a material. There's color, there's how metallic something is, how specular something is, how rough something is, how emissive. So to access this, I'm going to actually launch Super Florida Man on the side. This is the project that the club is like working on if you want to, right? And we'll go through exactly what that looks like. So here's Super Florida Man right now in its current state. So got this environment. All these objects have materials. Let's look at this. Let's look at this balloon here. This balloon's a really good example. This balloon is a 3D model that was exported from Blender. You can see these are the two material slots over here on the top right. M_base_balloon, and let's see, yeah, M_base_balloon and M_base_balloon string. So these are slots. Like I can remove things from the slot, and then it just fills in with Unreal Engine's like error material, which is this grid pattern. When there's like no material in something. This string has a separate material ID for it. So it's like associated with the bottom slot. So the bottom slot, I've created a material instance called balloon string, and it's this like white color. That's it. That's all there is to it. And then for this slot, I've created a material instance called balloon, just balloon, and it's this shiny reflective blue thing. By the way, credit to Marissa, she produced this balloon. There's just a good example. These are those material instances. So let's talk about what that means. To create a material in Unreal Engine, just down here in the content browser, you right click and you do material. And we can name this material. I'll call it my material. Okay. And this is how you access that interface that we were just looking at in the PowerPoint. So you can see here's like the node editor, and there's the palette over here, which is like different things that you can like drag in if you want, but it's a lot easier to just right click and search. You can see there's like a billion nodes. Each of these nodes corresponds to a chunk of code, and that code is called HLSL, and it runs on your graphics card like per pixel. It's fascinating how this works, but I won't go into the details too much. So I'm gonna close out Blender. I hope everyone understands this idea that like a material slot is associated with each face of the object, and like while you're modeling it, you define what materials go where, and then in Unreal Engine you fill those slots with whatever you want. I hope that makes some sense. Wow, what an incredible looking balloon. Yes, Shank, this is recorded. I am definitely recording right now. We're 9 minutes in. I heard Super Florida Man Game of the Year for really good Lamppost. That's funny. I'm sorry, Julie. So here we are in the shader editor. Before we move on, let's talk a little bit about some data. Also, the outputs, the ones that really matter are this like top 4 over here, and the rest of these get a little more complicated. So we're going to focus on the top 4 for now, and we'll get into the rest of them as we get later into the lesson here a little bit. Before we talk about outputs, we need to talk about data. Pixels on your screen you might be familiar with this idea of them having color values that go from 1 to 255. That might be a familiar concept to you. But what you should understand is that it's not in shaders, it's not going to be to 255. It's going to be a 0 to 1 value. It's going to be a floating point value that's 0 to 1. That's cool, William. Thank you. So each pixel displayed has 3 values, red, green, and blue, and they go from 1 to 255 on your screen because that's how 24-bit color data is stored. There's like 8 bits per channel. Like red, green, and blue gets 8 bits each, which 8 bits can describe a number up to 255. For our purposes, the range is 0 to 1. So instead of 51 on red here, it would be like 51 255ths. Like whatever that is, like 0.2 or something. Actually, that's exactly 0.2, isn't it? It's 5 times, yeah. So yeah, this would be like 0.2 for red, and this would be like 0.19 something, and 0.18 or something, I don't know. So back to the node editor. Now that we understand that pixels are, colors are not described as to 255, but they're described as 0 to 1, let's talk a little bit about some more data types. There's data types like 1 vector and 2 vector, and 1 vector, 2 vector, red vector, green vector. In materials, data is passed as vectors or vector fields. What is a vector? It's a magnitude and a direction. Like imagine an arrow, right? We all kind of hopefully know what a vector is. But in materials, it's got more than one number in it, and that can mean it can be a single a scalar. It can be, yeah, here I'm kind of losing my train of thought to describe this appropriately, so I'll just follow my PowerPoint here because I was definitely being clear when I was making this. Vectors can be described as colors or directions. How do we describe a color? With 3 numbers. How do we describe a 2-dimensional direction? With an x and y component, 2 numbers, right? You say like, how much does that arrow go in the x direction? How much does it go in the y direction? That's a vector. How do we describe a 3-dimensional direction? With the x, y, and z component, 3 numbers. 3 numbers describe a direction and magnitude in x, y, z. If I give you RGB equals 001, what color is that? Blue. If I give you RGB equals 101, what color is that? Purple. It's like red and blue. What direction is that? Blue is straight up. Purple is like 45 degrees with the ground plane. It's like 45 degrees with the, yeah, with like the ZX plane. So back to the node editor. How do we give our material color? We define color with 3 numbers. What has 3 numbers? A 3D vector. We call these 3 vectors. This is like a really universal thing in HLSL. The thing is, I'm only saying this to give you some idea of what's going on behind the scenes here. But as we move forward, you won't have to understand this super well. Like this vocabulary doesn't really show up, but it's important to kind of know what's going on. So let's color our material. When you hold 3 and you click, it creates a 3 vector node. So I can go to Unreal Engine over here, and I can actually just look up 3 vector, and here's a constant 3 vector. Or I can hold 3 on my number, like on my keyboard, and click, and it generates one every time I click. These are vectors. If I click on this, over here we get the data for it. It's RGB 000 right now. I can double click this and give it a color, you know, and be like, okay, blue. And I can drag this, you know, my mouse double clicks, it's very broken, into base color, and I can click save, and saving automatically applies. It's kind of like compile and save in Blueprints. And there we go. That's our material right now. It's blue. Sick. Very awesome. What we've done is we've plugged in a 3 vector. What is this vector? 0, 0.683, 1. That's, you know, it's got this value, and this value into base color. And that defined the color. But color and direction are sort of interchangeable, and we'll see how that makes sense quite soon. So here's an example of what we can do. And yeah, you get, you know, just color. don't worry about this metallic and roughness. So let's look at this material. Quick exercise. Like looking at this, just looking at this image, like, can someone tell me something about this material, just for fun? Let's do a little something. I'm looking at muted mics, but you can also unmute. It would be cooler if you unmuted. Marissa says it's a little shiny. Marissa's on the right track. That's a good word. It's shiny. It's rusty, smooth. Okay, so yeah, these are all properties of this. So how shiny it is described by two different values, and we'll talk about those. They're really fundamental to physically based rendering, which the acronym for that is PBR, and you've probably seen it a lot in game dev, like PBR renderer. Let's look at this trend here from left to right. We're going from this like gold foil look to like just like chrome dome. That is roughness. So this is not rough at all, and this is like very rough. It's like its surface has little microscopic like holes in it or something. That is roughness. That's not, no, these are all the same metallicity, but roughness describes like shininess, sort of. Metallic describes how, it describes, I believe, like how much of the light gets reflected. I don't know off the top of my head, honestly. Metallic and roughness. So roughness and metallicity, these are both one-dimensional values. How rough something is a 0 to 1 value. You're going to say how rough something is. You're not going to say what color roughness, what direction roughness. It's just how rough. It's a 0 to 1. Matte correlates more to roughness, Marissa. Metallicity correlates with you'll see. I'm going to show you a really nice diagram in a second. So therefore, roughness is determined by a single number, 0 to 1. A scalar. It's not a vector, it's a scalar. Or it's a one-dimensional vector, you could say that, right? But it's just one number, it's one number. Metallic is the same. Metallic is also described by one number. It's not what color metallic. Color is described by base color. Metallic is just how metallic is the surface. How rough is the surface. So how do we add single number inputs to our node editor? A 3 vector has 3 numbers. A 1 vector is of course a single number. To add a 3 vector, you hold 3 and click. To add a 1 vector, you hold 1 and you click. Really nice keybinds if you're trying to be quick in here. Just hold 1, I can click around, and every time I click, while holding the 1 key, it generates a 1 vector. I made this one big because it double clicked, because my mouse is stupid. So, this is a 1 vector value right here. I'm just gonna drag it into roughness. Roughness by default has a value of 0.5. That is why you might have noticed that this sphere has a little bit of white in the center, and it's kind of like dimmer on the sides here. Like it looks like it's, oh god, my mouse is clicking so much. You can see right there that white highlight on the edge of the sphere. That's because it's not completely rough. The moment that I plug 0 into roughness, watch what happens. Completely shiny, absolutely polished surface. This is like plastic, right? It's not metallic at all. Metallicity is a really accurate description of like a surface. It seems that like surfaces that are conductive have different visual properties, like just definitively. Dielectrics like rubber and like plastic, things that are insulators are not like metallic. It's just, you can go online and you can look up like real values. So let's like plug in another thing for metallic here. By default, metallic is 0. But if I set metallic to 1, this is going to become a chrome dome. Yeah, that's metallic now. That's fully metallic. What changed? Let's look at like 0.5 metallic and save and apply. Oh, you have bidirectional scattering distribution function. Nice. Yeah, BSDFs. You'll see BSDF used in Blender a lot. What Michael just posted is a really cool Wikipedia article on the subject. You don't need to know the math behind this, but understanding it intuitively is nice. And we'll go over intuition by just staring at this chart. Here's a nice chart. This is roughness from 0 to 1. This is metallicity from 1 to 0. So this is like a fully rough but metallic object. And this is a fully rough and not at all metallic object. And then this is a completely smooth and fully metallic, completely smooth and not metallic. You see, it's sort of metallic almost seems to describe like how much of the color of the surface is used in the reflection to a degree. Like you can see the reflection goes from like literally the ambient color down to the color of our surface times the like ambient reflection. Like you really don't see as much of the color anymore. I don't know if that's a good way to think of it, but it makes some sense. Yeah. Cool. It's a nice little side point here. One-dimensional values are visualized as black and white. Two-dimensional values are typically just shown in like a normal color sort of way, where its x and y are just red and green. So like a 2D vector will just look like some combination of red and green with no blue. Whereas a one-dimensional vector, you'll see it just seen as like black and white in Engine. Like let me just to show you what I mean by that. See this right here? This visualization is a full color. This is visualized as, oh, actually by default it's visualized as a red color. Interesting. So a one vector, like a scalar, is it's treating it like it's the red channel of an image. So what I said kind of no longer holds true. Right. By the way, you might be thinking, oh no, he left nodes hanging around. Are these adding to the lag? Are these affecting the efficiency of what he's creating? No, they don't. Not at all. Having these around. What's up, Michael?
The value associated with the color, like if you change 0.5, because it might be a hue saturation value.
Nope, it's the value associated with red, because it's the first channel. It's like XYZ RGB. So this is kind of just the X. The sphere makes me want a Baja Blast. So is that the material on the balloon right now? Will it make it shiny? Right now it's not the material on the balloon, but I can apply it to the balloon. In fact, let me do that. I can literally just see, I have the balloon selected right here. This is an instance of it in the world. I can just drag my material over here, and there it is. Now this specific balloon has that material applied. It's just the other ones have a very similar material. And it might be identical, honestly. I'm not 100% sure. It looks pretty comparable. So yeah, could be. Okay. Okay. So what do we know so far? Colors are defined by 3 numbers, RGB. N-dimensional vectors are defined by n numbers, right? 3-dimensional vector, 3 vector. 2-dimensional vector, called a 2 vector. 1-dimensional vector, Unreal Engine likes to call them 1 vectors, I think. Like if I right click and I look up 1 vector. Nope, never mind. Good, it calls them scalars. Or does it? What is this called? Constant, it calls it a constant. Yeah, my bad on the vocabulary there. It's not a big deal though, but yeah, just, you guys get it. Like if I press 2 and I click, there's a 2D vector right there. And if I make this, you know, a little bit red and a little bit green, it gives me this like yellow color because there's no blue to it. Sick. Okay, let me, oh, God, my mouse. There we go. All right. Okay, cool. So, we also learned that vectors represent directions or colors in the context of materials. It can be either. We'll talk about directions more. The base color material output takes in 3 numbers and controls color. So that output, right? This guy up here, base color, 3 numbers. If I plug in a single number for him, what do you think he's gonna do? What he's gonna do? That's 0 right now. What do you think is gonna happen when I put in 1? It's white. It goes white. Because it just takes this and it applies it to the XYZ. Like it fills all 3 of its holes with the 1. If I put it 0.5, it's just gonna be gray. Whereas metallic here and roughness are like 1 hole, 1 number to fill. They're expecting 1 number. If you plug in a 3 vector to these guys, I kind of don't know what's gonna happen. It might only take the first component. If I put 1 on metallic like that, there we go, it became metallic. What happens if I change this one? Nothing changes. So yeah, it's literally just reading the first component of the vector there, the first number. So yeah, metallic expects a single constant. Roughness expects a constant. Specular expects a constant. Anisotropy expects a constant. Anisotropy is an interesting thing. If I crank up anisotropy, you'll see that it should start. Oh, never mind then. 0.5? Hold on. Anisotropy is like the effect that you see on like a pan or a CD, like a disc, when you look at it and it has that like weird kind of holographic effect that's aligned towards the center. It's a really weird effect. Did you lock yourself out? Hold on, my roommate totally locked himself out. 1 second, guys. You're fine. Okay. All right, I'm back. Ugh. Okay. Don't worry about anisotropy. It doesn't seem to be working here, but I'm not sure how that works. But we'll play around with that. It's not really used often. Very special use case. Okay. Some important final notes. Roughness, base color, and metallicity are clamped. That's a good one. So if you input 99999 to roughness, it's the same effect as inputting 1. If you input a negative number, it's the same effect as putting in 0. Like, if I plug in, like, you can type in a huge number here, 99999. It's just that. It's going to be just 1 metallic, nothing special. If I plug in to my base color, a color, when you're using the color wheel here, guys, it only lets you go to values between 0 and 1 on all 3. But if I actually manually type them in, I can go 999 on green and like 200 on blue, and that's it. It gives me like a combination of those colors, but it's not anything excessive. You know what does not clamp the input? Emissive color. Emissivity is how you make stuff glow. So if I plug this, oh my god, my mouse. If I plug that in there, oh yeah, oh, she's glowing. So what it's doing is it's injecting those values into the bloom filter on the screen. Bloom is the effect of giving things glow on the screen. It's like a screen space shader. So it goes, hey, these pixels are glowy, so I will take the surrounding pixels and I will apply an effect to them based on just how glowy these pixels are. So you can see that's bloom. And the moment that bloom exits the screen, that glowing effect is gone. There's no glowing effect on the screen anymore unless there's a pixel there to create that glowing effect. And you can see it's not generating light either. It's like this fake effect of something glowing. It would only generate light if you do RTX, which is like ray tracing. Then you can say, hey, let the emissive material inject photons into the world, and it'll respond accurately. But don't worry about that too much. Just that's what emissive does. It makes stuff glow. Okay. All right. That's a quick introduction to materials. Very quick introduction to materials. So let's get to the interesting stuff. Let's get to the really interesting stuff. Let's talk a little bit about textures and dynamic materials. I hope the background noise isn't too much. It's a little distracting to me, unfortunately, but that's my problem. I'll work around that. Texture coordinates, the LERP node, material instancing. We're gonna go over a lot. Right, in Unreal Engine, the range of colors are 0 to 1. 3 numbers can describe a vector. That's red. You know, 1, 0, 0 is just an arrow pointing in the positive X direction. This is like review that I gave people back in the day. All right, textures. What is a texture? A texture is an image file. You might call a texture a vector field. Why would you call it a vector field? Because it is a series of vectors, or colors, and each one has an X and Y location. It's just like a bunch of pixels, right? And those pixels have an X and Y location, and then they have a 3-dimensional vector associated with them, which is just a color, RGB. It's a giant grid of 3D vectors, each pixel being a 3D vector of color. What can textures look like? They can look like a lot of different things. This guy over here is colored, believe it or not. This is supposed to be like an example of a colored texture. This over here is a normal map. We'll talk exactly about like what those are and what they do. This would be like a roughness map or something, and it's grayscale. I know it looks like this guy's not colored either, but he is. He's got like a little bit of brown to him. This guy's just grayscale. This guy's grayscale as well. what do textures do? Here's an example of a material that's utilizing textures, and here's an example of a material of that material in the world. You can see that the textures are kind of helping contribute to the shading. As I move a light around, you can see that the shadows, there's little divots and holes on the surface that respond accurately to the light source. And they make it look like the surface is three-dimensional when it's really not. It's a perfectly round sphere that has a normal map applied. Normal maps create that effect. So, an important question. How do they know where on the surface to be? How does a texture know where on that surface it belongs? Like, should it be a little to the left, a little to the right? Should it be bigger or smaller? Does it repeat? You know, these properties are defined by the texture's coordinates and by the model's UV map. How does a texture pixel align itself correctly to 3D geometry? So, quick review. In Blender, we have a 3D model here on the left. Here's an example of a lamppost. Julian, take notes. I'm sorry, I'm completely joking. But this is that lamppost UV unwrapped. What does that mean? It just means that it's been cut up into 2D surfaces. So this is those 3D surfaces cut up into 2D. You can see that it's like, for example, this frame right here is like this frame, and this panel here looks like one of these 4 panels. Like, these 4 look like different panels from around here. And so what we've done is we've taken a 3D object, which is a bunch of 3D points with 3D positions, and put those points on a 2D plane. And now each of those points has 2D positions, and the positions between them can be described as like positions along, you know, just aligned to the different parts of the 3D model. So here's a texture applied to those coordinates, and you can see that texture on the left here. So you can see what's going on here, like H2 over here. Let's see if we can spot it. H2 looks like it would be one of these panels. I don't see any H2s, but it might be on the back somewhere. The bottom is this panel over here, I think. So when he goes to the bottom, we should see G5. There it is. There's G5. That's G5 from right over there. So yeah, in fact, here, let me turn on the laser pointer. G5 over here is going to be right on the bottom, right there, G5. So yeah, that you kind of understand what's going on here. We've taken a 3D object and its points and geometry have been described on a 2D plane. And then we can associate a texture with that 2D plane, and the texture will populate those surfaces in 3D based on like what the 2D position of that surface was on the texture. So, you know, here's this panel. See, I can like move it around and, you know, just kind of move it to different spots. I can rotate it. Yeah, this point has a 2D coordinate on this grid, like 30,5. This one might be like 33,5. This one might be 33,3 and 29,3. What does all of this mean? 3D geometry is associated with a 2D grid. It'll check that 2D coordinate to read a pixel on a texture. Knowing this, we can now mess with the texture coordinate node. So you don't have to do any of that, you know, if you don't want to. That's for the 3D modeler to do. They UV unwrap it. Your job as someone that's like making a shader is to understand what texture coordinates do. So this texture coordinate node here, you know, think about it for a second. What is the value of this pixel on the top right corner right here? It's like completely red. It's going to be like 1, 0. You know, completely red, not at all green. 1, 0. That's X and Y. Over here, black, 0, 0. Over here, 0, 1. Red 0, green 1. Over here, 1, 1. Right? 1 on the X, 1 on the Y. So this is a coordinate grid. It's just a mapping that says, hey, you know, this is your position. It says, hey, the pixel that's the top right of this square is going to position itself on the top right of the UV map, and this one's going to position itself on the bottom right of the UV map. and so on. So that, yeah, 0, 0, 1, 0, 1, 1, 0, 1, 0.5, comma, 0.5 in the middle. What if we could manipulate the grid that textures read? The textures apply themselves to this grid by assigning a UV position to every pixel. If we mess with a UV position, we mess with where the texture's pixels go. So, right, texture kind of aligns itself to these coordinates. What if I add 0, 0.5 to every number? Then it becomes this, right? So if I add 0, 0.5, that's x, y, I am shifting this along the y-axis. I have effectively made everything a little bit more green and a little bit more on the y-axis. And now the entire coordinate grid has shifted to the right. So what happened? Our UV grid shifted down, I guess, actually down, yeah, because the y-axis is like up and down. So we added 0.5 to the y component, which means we shifted the UVs down since positive y points go down. Guess what our texture did? The pixels looking for 0, 1 are now higher on the grid because the top left isn't 0, 0 anymore. It's 0, 0.5. The bottom right moved up by 0.5. Every pixel moved up by 0.5 units, 0.5 being like 0.5 UV grids. It's almost like the equivalent of moving that UV grid of a model down. Like, okay, let me just... Essentially what we've just done is we've taken this and we've moved it, like, down. But instead of moving it down, we actually, like, moved the texture relative to it up. That's kind of what's going on here. This is just, like, prefacing just some understanding. Here's Phil Swift, and here's me changing how much I'm adding to the UV, to the texture coordinates. The texture coordinate node. So if I'm adding on red, you can see we're shifting left and right. If I'm adding green, we're shifting up and down. This is just a plane that's been unwrapped. So yeah, here's Phil Swift on a sphere, and the sphere has the same, it's got texture coordinates. So this is what I just did. This is like exactly what I just did. Is these nodes right here? This is a texture coordinate, and I hope I sound clear. My roommate is vacuuming. Anyways, we're adding the red and green values here. What is this mask node doing? It's isolating the red and green values. It's grabbing only the red and green values, not the blue value. It doesn't matter if we added the blue value from this. Like this right here is a 4 vector, no. Yeah, 0, 0.5, 0, 1. Yeah, this is a 4 vector node. So this has RGB alpha, right? RGB alpha. And what I'm doing is I'm taking all of its colors combined and I'm isolating the red and green with this mask. This is a component mask. So it's just grabbing the 2D vector from that and it's adding it to this 2D vector field essentially, and then applying that to the UVs of a texture. So very important, everything uses UVs, everything. Base color applies a color to the whole surface, but it still turns a single vector into a whole field. This significance gets obvious when you want to isolate bits of your surface and you realize it's all vector fields. This kind of starts making sense soon. I'll show you some cool tricks really soon. You are going to need to UV unwrap your capybara. Yes, you are. That's a very easy process. You can do it in like 1 click, honestly, if you want to. Yeah. Yeah, A and then U, exactly, and then smart UV project. So we've gotten over manipulating texture coordinates. Let's talk about the LERP node. Here's Bill Mays from OxyClean. LERP. This is the most important node. This is one that we should really talk about. Let's go in Unreal Engine. Okay. If I press and hold L and I click, it generates a LERP node. What does LERP mean? It means linear interpolate. And it gives you a really nice description here. The linear interpolate expression blends between 2 input values based on the 3rd input value used as a mask. This is, in digital logic, this would be called a mux, I think. I mean, like, it's common everywhere. It's just saying, if alpha is 1, output B. If alpha is 0, output A. Okay? So it just picks one of these based on alpha. And it will linearly interpolate between the two based on what alpha is. So if I put in, let's say I put in color, and that color is like this blue hue, and then I grab another color and I make it this green hue, and I plug this into B, and I plug this into A, and then I plug in a scalar, and the scalar is 0 right now, and I plug this into base color, and I hit apply. What's going to happen is it's going to output A. We're just looking at A. If I change the scalar to 1, it's going to output B. So it picks B. This green value comes in. But if I set this to 0.5, now it's outputting halfway through between these two colors. LERP is just fundamental. It is used everywhere. The LERP node is really, really important. Linear interpolate, that's what it comes from. LERP. Linear interpolate. LERP. Here's, all the stuff with Phil Swift and his shifting texture over here. And then is Bill Mays. And there's a parameter called God versus Phil Swift. And if I change this to 1, it'll output the shifted texture of Phil Swift based on however much I've shifted it. Or actually, if I change it to 1, it becomes God. And if I change it to 0, it's Phil Swift. Here's me playing with LERP. Notice when LERP is this stupidly negative value, it's like absolutely blasted. It's like JPEG'd and everything. Why is that? That's because it doesn't really, it's not intended to expect like more than 0 to 1 values. Don't like make it less than 0 or more than 1. Clamp your inputs to LERP. But it's not clamped. It's like over going in one direction over the other. I'm not really sure what the math behind it is, but there is some like math that would explain this artifacting. So yeah. What's artifacting? I might use that word frequently. Artifacting is referring to like any visual errors that like it shouldn't be happening. LERP is simple. Alpha is 1, output B. Alpha is 0, output A. Alpha is 0.5, output 0.5A plus 0.5B. And now the creme de la creme. Material instancing / making materials from shaders in Unity. Weird vocabulary contradiction, but they mean fundamentally the same thing. There's something called a draw call. All you need to know is that draw calls are bad. A draw call is going, hey, look up data and like send it to the graphics card or something. Draw calls cost precious nanoseconds. Each material that you make, or each shader in Unity that you make, is another draw call. To reduce draw calls, we make instances of the material. This also lets us do more. It gives us some nice special features. Observe. Here's a standard run-of-the-mill material. It's got 4 textures here. It's got a texture for base color. It's got a texture for specularity. It has a value for metallic and a value for roughness. And it's got a normal map. And it's got a texture sample for ambient occlusion. It's just another texture. And they're all hooked up to texture coordinates. Cool. Brilliant. Standard run-of-the-mill material. This is a material instance. A material instance, let me show you in Unreal Engine. Here's our material, right? I right-click it. I do create material instance. And just hit enter, whatever. And now this is an instance of that material. It's identical to our material. And you're probably thinking, wow, that's freaking lame. Why would I just make a million copies of the same material? Like, why would I generate this like additional data? You're right. You're right. Right now, this is immediately useless. But watch this. I'm going to right-click this guy. I'm going to do convert to parameter. And I'm going to name it color A. I'm going to right-click this guy. I'm going to say convert to parameter. Color B. I'm going to right-click this guy. I'm calling him alpha. Right? Save and apply. And now watch this. We go back to our material instance, and those settings appeared on the top right. And now we can check these boxes to start editing them. And I can be like, yo, color 1 is going to be red. Notice it instantly updated. There was no save and apply. There was no compiling shader. It just instantly updates. And I can play with this alpha value to switch between these, and it just instantly updates in real time. So now I can make multiple instances of this right? So say we had like 50 different balloons. We wanted some red balloons and some pink balloons and some orange balloons. We can give them all different material instances, but they will all share the same draw call in the world, which is just a single reference to the main shader, the main material, and all the instances read from it. And it's like, it's more efficient on our engine, and it's also easier for the artists, because the artists just get to play with just these numbers. All they have to do is tinker with these basic numbers that you've gone ahead and named and defined the constraints for. Like you can go here and you can say, hey, the minimum value of this slider should be 0 and the maximum value should be 1, so that your artist that might not know what they're doing doesn't accidentally slide this to 9 trillion and suddenly their material looks like a JPEG'd Phil Swift. You know, they just limited it to 0 to 1. It's really nice to do this. Instances are like copies of a material with whatever things you've converted to parameters exposed. So a lot can be a parameter. A texture sample can be a parameter. I can call this what texture ? And plug it in here. So yeah, you can just do that. That got angry at me because I haven't actually given it a texture, and it's like, oh no, give me a texture that I can be, otherwise I'm angry. But yeah, a lot of things can be parameters. You can just right click on stuff and it'll be like convert to parameter if you can make it a parameter. Yeah, back to this, the incredible material instance. What are material instances? They let us expose specific vectors and textures to be edited at runtime while the game runs. That's another thing. Every edit that I was making to that material, the like original material, you cannot do while the game is running. But material instances, if there's a parameter exposed on a material instance that's like available to be edited on the instance, that can be changed while the game is running. So you can say like, hey, you know, Mario picked up the coin, run this like sine wave on the coin that makes it look like it just glows really bright for a second. You can do that. What does this let us do? It lets us create dynamic weather. We can say, what about snow that builds up on the surface of a like object and then goes back down? Maybe we want to change the ocean wave height with that weather. Wind direction can change during the game. We can save the player's location as a vector inside of material instances. So we can have an object that's constantly beaming out this data of where the player is in the world, and any material that has that parameter is going to be like reading from it. So you can change these things in real time inside of the materials. TLDR, they connect external events to our code and let us save draw calls. Like material instances are amazing. We should use them everywhere we can. You don't want to use the original like material on an object unless it's like a one-off case where you're not gonna do anything else. Yup, you can make material instances, and then inside of the instance you can like edit different parameters. Instances versus raw materials. Materials, whenever you do save and apply, it takes forever if you have like a laggy GPU or CPU. You can't edit them at runtime. They cost a draw call. There's literally 0 advantages. You should only make new ones for like really special use cases. So like what we've done in Super Florida Man is we have a master material, which is just to say like a really one material that most of our objects can utilize. But when I delete this, it's going to get angry because this balloon, but you know, it just goes back to its default. So if I go to models, here's our master material. This guy. This is our master material, and it has parameters for the different textures. And it also has these switches that say, hey, use a solid color instead. And from it, you can make a material instance and plug in your textures, and it'll work for just about any object, because most objects, all they care about is a couple of textures. So you're just like, okay, here I go. Okay, here's I want a different texture for my color, and I want a different texture for my materials, roughness and metallic, and a different texture for normal map, and maybe I want to play with the roughness and the metallic, and that's it. You can make a million of these for every texture, and they will all use one draw call. Incredible, amazing. Saves us time, saves us effort. Really convenient. There's only rare cases that you want to like, you're like, oh no, this is way insufficient. For example, grass. I'm just gonna give you like a quick glimpse of what grass looks like. The grass in our game is very special. It has to wave around. And it's got subsurface scattering where like the light kind of bleeds through its surface and it glows a little bit. And it has to fade out in the distance. So it does that. It kind of does this dithering. And see, there it goes, it faded out. And the density changes based on how close it is to the player. And it should deform around the player. And like a million other things. So grass is like a very special use case. And it has all these extra properties that need to be described in the material. So you don't use that master material for it. Instead, you have to go and make your own material. So here's the grass shader, right? Much more complex, has like a bunch of stuff going on in it. It's not that complicated. It's not, I promise. But yeah. Okay, and we're gonna like totally make a water shader by the end of today. Wow, it's already 5:12. Frick, man, I'm so excited. Teach us the grass texture, you heathen. I'll go into it. Yeah, here's an example of material instances. Cool. Right. Let's talk about dot products and vertex normals. That's really important. What's a dot product? It's like multiplying but vectors. But more importantly, it can tell us the angle between two vectors. So, what do dot products do? They are actually a big part of lighting. If I say, shade this surface, shade the color of this surface based on the dot product of the light vector and the surface normal, well, the surface normals here are going like this way, and this way, and this way, and this way, and this way. And they're all these normalized vectors that run, you know, orthogonal to the surface. And if I compare them to the opposite direction of the light source, this guy is in agreement. He says, hey, I'm facing in the same direction. So he outputs 1 if I do dot product of these two vectors. If I dot this guy, who's facing 90 degrees from the light vector, because the light vector is going this way, right? This guy would output 0. And this guy that's facing in the opposite direction of like the negative light vector, right? Because we're flipping the light vector. Yeah, the light vector is coming in this way, but we're pretending that's not. Pretending it's going the other way. This guy would output -1. That's really useful. That's really, really useful. Say you want snow to always build up on the top of a mesh. Done. Say you want a different texture on the surfaces that face up and a different texture on the sides. You know how I'm doing the terrain in here? With a dot product. This terrain automatically fills in a different thing for slopes, right? So I can literally just go here in the terrain editor and I can be like, and look at that. It automatically adds a different texture for slopes. And it also describes where the grass should go based on the dot product of the slope with the global up vector, of the surface with the global up vector. So that's, you know, dot products, like very useful. It's saying like, hey, you know, this is facing sideways, so not good, but this is facing up, so good. And this is facing up, so good. And none of this can ever face down because that's just the nature of terrains. Cool. Wait, undo that. I like that hill. Thank you. Okay. Vertex normals, right? How do we access vertex normals in materials? There's a node for that called vertex normal world space. And WS is referring to world space, and this is what it looks like. So points that are facing to the right in world space get like, you know, positive X, and that are facing to the left get like 0 on the X because it doesn't go negative. So 0 is like negative. 0.5 is 0, and 1 is like positive, if that makes sense. Like, well, we'll see. Yeah, this is like not, this is like technically correct, but in the game engine it would actually be 1 and then 0 here and 0.5 here. You see what I'm saying? Like instead of negatives, it's just 0 to 1 is the range. So it goes 0.51, 0.51. Here's an example of a shader that you can make that applies snow to the top surface of a rock, and only the top surface, so that your artist can just drop a rock in the world, and no matter what angle they place it in, snow will gather on the top surface. Beautiful, amazing, cool. All right, grass and oceans. Let's freaking go. Do we make a grass shader together, or do we make an ocean shader based on my PowerPoint? I'm not gonna make you guys like walk through it. But this PowerPoint is way more thorough. But I will go over the grass. We'll speed run the ocean shader. Because if I don't wait for you to like do it because you're not following along, which I don't think anyone's following along, and that's fine. That's intentional. This is more of just like a throw it at the wall, see what sticks kind of thing. That's okay. So, okay, cool. Let's look at oceans. We're gonna make this shader together, but not really, but like kind of. We're gonna walk through this shader. What is this shader going to ultimately look like? It's gonna look like this really nice water here. It's like rolling around. It's very pretty water. Yeah. Cool. This is what we're gonna make. So, let's get started. The first thing that I like to think about is, right, I gave my students like a Unreal project and they opened it up, and I was like, yeah, just work on the material with me, right, to save time. Right, 3-vector node, cool. Blue water, amazing, done, right? I mean, that's basically water. It's blue. No, there's more. There's more to water. Let's talk about water. Let's talk about something. Let's look at some pictures of water, right? And talk about some of its properties. That's like the first step here. Water skiing on gators. Thank you, autocomplete. Right. Here's some water. Let's look at, here's a picture of something that we would kind of want to make. So, some properties of the water here. It's obviously very reflective. You know, very like, it's got that metallic kind of quality to it where the reflection is much of the color of the reflection and not necessarily the blue color of the water, at least in the reflective spots. It's got these like highlights. Another thing that we're noticing is that when we're looking into the water at a distance, at an angle, it's this nice light blue sort of color. Whereas when we're looking down into it directly, it's this dark blue sort of color. And we can kind of fake that effect by saying, what angle is our camera looking at the water from? Versus what is the up vector of the water at that point? And by comparing that, we can shade vectors of the water that are farther away as like lighter blue, and ones that are really close to us that we're looking down into as dark blue. So we're gonna start with that. Notice the pattern along this orange line. When you're looking water down into water, it appears lighter than farther away. Water that you're looking down into appears lighter than farther away. Right. The idea here is that light has to be in the water longer, like farther away, it's kind of just being absorbed more. I'm not sure if this is 100% correct, but like this is how depth kind of is done. This is a Fresnel node. Fresnel is, you might have heard of Fresnel before. I think it's used in like lighting or something. I'm not 100% sure. But yeah, Fresnel lenses perhaps. But here's the effect that it's having on this plane. You can see that when the plane is looking 90 degrees from us, it's white, but when it's looking at us, it's black. Like it outputs black for surfaces that are pointing straight at us, and white for surfaces that are pointing away from us. So when I switch it to the sphere here, this material is applied to the sphere, you can see the edges turn white because they're pointing away, and black because they're pointing like into us. So what we can do is we can use the output of Fresnel to interpolate between two colors, a bright color and a dark color. And there we go, we got this like nice kind of ocean effect where it's dark blue in the distance and light blue when we're looking like down into it. Nice, right? That's a good start. Good start to water. Let's get the water to be a bit more shiny. Metallic and roughness. I set the roughness to 0 and metallicity to 0.5. Beautiful. Now it looks shiny. Before I move on, I make a material instance. Just to like have it around. The material instance will update with the material depending on what we expose, and you know, but whatever we do to the material will influence all material instances. So now, back to the material. For the instance to be useful, we need to make some parameters. So I go over here and I make a roughness parameter that I can play with in real time, and a metallic parameter. And I make a parameter for the color. I call dark color and light color so that I can actually manually control them. And I go over here and I set those values to what looks good by actually playing around with them in the engine and seeing what looks nice. And I decide that roughness at like roughly 0.16 looks good, and metallic at 0.2 looks good, and I set the light color to this kind of green color that water looks like, and dark color to like a darker blue in the distance. Now, something you're probably noticing that we'll talk about real quick is you're probably seeing this weird effect here, right? This weird edge here. This is because of screen space reflections. In video games, there's different ways to handle reflections. There's photons, if you have RTX on, right? And a photon will actually like fire a photon from the camera pixel into like whatever it collides with, and then it'll bounce it off into the distance, and it'll be like, oh yeah, this source is gathering the light from these different points, and therefore it should be shaded this color. And you'll get accurate reflections. But the cheapest technique for reflections, the most computationally inexpensive technique for reflections, is screen space reflections. And what it's doing is it's just saying, hey, what's already on the screen? This like cloud over here. And it's going, oh yeah? And this surface is like kind of up, and the camera is like here, so the camera's bouncing into it, and therefore it's landing the ray somewhere like here, so therefore I'm going to reflect what's on the screen. And it just takes what's on the screen and it puts it in the reflection. But it only works on what's on the screen. So as I move my mouse down, as I like look down, less and less of the sky is visible, and this reflection will start fading out into like just this area reflected and then nothing at all when I'm looking straight into the water. It's a very cheap effect. It's not able to reflect anything outside of these edges because from the camera to this point, the ray bounces off into a sky that is not on the screen. So it can't fill in any of the data there. So it's just like, I don't know what the frick to do. And it just does that. Reflections, real-time reflections at least. There's also static reflections that are done by using like reflection captures, which are just like 360 cameras that are you kind of place in the world, and the engine goes, oh, I'll read what the 360 camera sees and use it to generate some fake reflections in the area. Yeah. So back to our material. Let's make some waves. So what I do here is I check a box called Show Engine Content. Whenever you're in a menu in Unreal Engine, like over here, actually let me go in here. If I select like oh, I don't know, this texture, right? And I go here and I'm in one of these drop downs. This is like a frequent type of menu that you encounter in Unreal. That's a button on the bottom right called View Options. And in View Options, there's a checkbox called Show Engine Content. If I turn this off, I will only see things that I have created for the game world. But if this is checked, I see things that the engine is using. And believe it or not, the engine is using a lot of the same assets that your game might like similar, functionally similar assets to what the game that you're making utilizes. So like it's using textures and HDR files and all that, and they're all in the engine. Like when I switch to sculpt mode and I'm moving this around, this is actually a plane that is being placed at my mouse cursor, and that circle that it's generating is a shader. It is a material that is being applied to that plane, and it's reading in data from this like radius value and this fall off value to generate this nice circle for me. Yeah, that's a shader. And in fact, if I looked around, I would be able to find it in here. But when you check Show Engine Content, you also get access to a few more nodes. One of them is called Motion. Never mind, hold on. Material function, right. You create a material function call. A material function call is just like calling a function in code. It's calling like an external material. And what I'm gonna call here is four-way chaos. And motion underscore four-way chaos, if I double click this, it'll take me to that material function. A function has like inputs and outputs. It returns this given these inputs, a texture coordinate, a speed, a texture, and time value and some other things, and it outputs this final texture. What it's doing is it's taking one texture and it's moving it in 4 different directions, right? Up and to the left, down and to the right, up and to the right, down and to the left. And it is overlaying these 4 textures to create this effect that you see on the left. It's taking this texture here, which you can see, it's overlaying them. Notice how that kind of looks like water. It looks like crazy chaotic ripples going in every direction. So that's what we're about to do. motion underscore four-way chaos. Very useful node. It just saves you some time. Yeah. So where was I? Right. So that's what I do over here. Create a motion underscore four-way chaos. And I get a normal map. A normal map is describing the direction that the surface is pointing for every position on the surface. So it's giving it like a fake direction to point. And I take the normal map. You have to convert it to a texture object. I'm not sure why that is. I don't quite recall something about texture objects not being parameterized. I have a feeling William might know that. Or maybe someone else. I don't know. Pressure. I just like, it seems like a random thing that someone might know. And yeah, try right. Please ask. You can chime in. And then yes, and then I plug that into the normal output of the material. And here it is. Here's water. So there we go. We got our water. Now that water is looking huge. Those ripples are massive. Okay, let's fix that. Remember what we said about texture coordinates? How they were 0 to 1, 1, 1, 0, 1, 0 on like the top right corner. If I take those values and I divide them by like 30, then the texture is going to like try to squeeze itself into a much the texture is going to sort of like scale itself down, I guess, or in a way like the UVs scale themselves up when I divide those. So that's what I'm doing right here. I'm taking absolute world position, which you can treat kind of like texture coordinates, and dividing them by scale. And what it's doing, while we're at it, I add a couple more parameters, one for speed. So this is going to be like the wave speed, wave 1 speed. And just like that, bam. And there we go. We have this repeating pattern. Now, our water at this point looks like PUBG water, which kind of goes to show how disgustingly bad PUBG's water is. It's just like this repeating pattern forever, and it looks ugly at a distance, yada yada. It's got like all these terrible effects. The reason why is because there's just too much repetition. It's the same exact pattern being replicated a trillion times. We totally already covered like broadly what a shader is. Yeah, sorry, try right. Earlier in the session. But I'm recording, so we're gonna cover that. Or you can go see that. The recording should be good. So what I do is I copy paste this whole set of nodes 4 times or 2 times. I add 2 more waves, or 3. Okay, yeah, 2 times for a total of 3. And you probably have a vague idea of what I'm about to do. I'm going to make small waves, bigger waves, really big waves. And the really big waves are going to travel really slowly. And the medium waves are going to travel medium quickly. And the small waves are going to travel really fast. Right, see what William just replied with. William has been taking some notes, which is awesome of him. So take a look at that. You have to rename the parameters. If you have a parameter that's named the same as another parameter, it's just the same. It'll just be the same value. Like the only thing differentiating them is the string that is their name. So that's important. And finally, I add one more 1 vector to the divisor value. Divisor is like dividing the vector. Or not the vector, dividing the texture. So it's taking this normal map and it's going, hey, make it lighter. And if we divide it by 3 and then we add 3 versions of it, it ends up adding up back to like a 0 to 1 range. You see what we're kind of doing here? Like if I added 3 normal maps, the outputs would not be in a 0 to 1 range. They would be in the 0 to 3 range. So by dividing them all by 3, which is what this divisor input for 4-way chaos does, then adding them together is a 0 to 1 range. And then off of that final node, so off of like this final add here, or this right here is the sum of 3 of these different wave generators that are just this texture being overlaid, but they're going at different speeds and different sizes. So off of that final node, we can add a way to control how strong our waves appear. And what we do is we mask out the red and green value and the blue value. Red and green is describing how left or right a surface is pointing on a normal map. Blue is describing how up it's pointing. The thing is, an engine processes the red and green values relative to the blue value. So if you say the surface is not pointing up at all, it gives more intensity to like how sideways it's pointing, sort of. That's a vague kind of explanation. So if I divide the blue value by like 2, then these red and green values are interpreted as pointing more left and right on a like normal map. What's exactly the difference between using a normal map for waves and using a superimposed sine wave? We're actually going to switch to a sine wave as well later in this tutorial. But here's our water now. Our water is starting to look really nice. Really, really nice. This is the small waves, little ripples, bigger waves, these little medium ripples that we're seeing, and then these big waves, which are these big patterns that kind of break it up. Really nice effect. Brilliant. Amazing. We have ripples, we have color, we have reflections. What's missing? Translucency, foam, and actual three-dimensional waves. This is where I'm going to do the sine waves in the second try, right? So, let's do translucency. Translucency is in the material settings. So what do I mean by that? Here's the grass shader. When I select a node, this panel over here, this details panel, it becomes, it's like what the node is, right? So like, oh, the switch, default value, texture coordinate. I can change the tiling, the texture. I can change things about this node. If I click in the blank space, it goes to the material details. These are like global variables related to the material. And there's a lot in here. There's physical materials that you can associate with it that describe friction for the physics engine. There's different types of like root shaders. You can say like, hey, it's a masked material or a translucent material, and these affect how the graphics card processes the material. Like masked is more efficient, translucent is complicated, and the graphics card goes like, oh no, I've encountered a translucent pixel. Let me re-render this pixel ignoring the object partially and superimposing whatever like percentage of translucency from the first impact was. There's like these different types of materials, and there's these different like pre-made shading models that are ready as well. Two-sided foliage is really useful for like grass. It's like an efficient version of subsurface rendering, or subsurface shading, subsurface scattering. So what I'm doing is I'm going to go in here and I'm going to change this to translucent is what I do. So that's where that setting is. It's inside of the material settings. You just have to click nowhere, have no node selected, and then you get all of these settings related to the material. So I go over here and I change it to translucent, and I check screen space reflections for translucency, and I change the lighting mode to a surface translucency volume so that it interprets it like a volume even though it's just a surface, right? Does that make some sense? So like it pretends that there's water below the surface of the water visually. Like that's kind of how it'll interpret depth. Translucency can mean different things. It can mean like just a 2D plane with no volume behind it. Anyways, first things first, let's change the color based on depth. Our goal is to have this like tropical effect here, right? Where like the shallows get the sandy turquoise, and the depth and deep areas on like Google Maps. If you've ever looked at like the Bahamas on Google Maps, there's these beautiful islands that are like this turquoise where the sand is, and then it gets deep and it just turns into this murky dark blue. Yep. So over here, I create another LERP node off of the color, right? We have all this stuff doing the color based on what angle we're looking at it at. Then I add another set of nodes, and I say switch between this stuff and a color for the shallows based on depth. How do we get depth? There's a node called depth fade. And what depth fade is doing is it's identifying the distance between where we first intersect visually with the water and where the second intersection occurs. First intersection, second intersection. So over here, it's got like a really low value, and over here it's got like a bigger value and a really big value, etc. So depth fade, you can change the default opacity, and you can change the fade distance, which is like what range it'll transition from 0 to the opacity like number, or from the opacity number to 1. I don't remember exactly. Like you can always mouse over these nodes and they tell you. In fact, here I'll just literally depth fade. Control Alt. There we go. Depth fade expression is used to hide unsightly seams that take place when translucent objects intersect opaque ones. That's true, But that's not the full story. So I click see full document. Oh, that's dirty. Oh, Unreal Engine, how could you? Oh no. Well, if you want, we could visualize this. I could literally just plug this directly into base color, and we could see what this looks like on our grass. I won't do that right now. I probably should have just made this water shader for Florida, man. We do need a water shader. That's on the to-do list. But oh, here's our grass. Our grass is compiling the shader again because yep, there it goes. Grass, brilliant. Okay. So right. So now this is what it looks like that I've added depth fade. We get this like partial translucency. It says like, hey, you know, cool. The shallow areas will look like that. Very nice. You may have noticed, however, that enabling translucency has made the opacity value not gray. Yeah, when you enable different like types of shaders or different shading models, you get access to different outputs, like opacity. Right? If a material hasn't been declared as translucent, it's not going to get opacity. It is more computationally expensive to be a translucent material. That's why it's not on by default. When you say, hey, treat this like it's translucent, then suddenly you get this opacity value that you can play with. And the material becomes significantly more expensive computationally to render. So seeing it in your field of view makes your graphics card just a little bit angrier for every pixel that is intersecting with a surface that has this material applied. Translucency changes with depth. So I add another depth fade and I say, hey, make it more translucent when it's shallow. So opacity fade distance, this is, I think, 100 centimeters or 1 meter. And the opacity is 1. So it says, hey, make it opaque at 100% depth, which is at 1 meter, and make it 0 at 0 meters, I think is how that works. And before we move on, I also add refraction. Unreal Engine does refraction in screen space. All you have to do is import index of refraction. You just give it a scalar value for index of refraction, and it works. And there we go. There's translucency at the water's edge. I don't know how visible that is to you guys, but that refraction looks very sexy. We got like, you know, the tiles of the default texture are like, you know, deforming visually. Very nice. Finally, big 3D waves. That's like the last step here. So Gerstner waves. What are Gerstner waves? Gerstner waves are how water behaves in real life. And fundamentally, like the water in Sea of Thieves is probably the single best example of water rendering ever. Like, God, just look at that. Look at Sea of Thieves water. Look at its water, you guys. Look at it. Freaking look at it. It's incredible. They're doing a lot of magic here. Like, so much magic. The water interacts with the ships, and there's multiple ships. There's like, it's multiplayer, right? So everyone has to be using the same waves, right? Because if somebody has like a big wave and someone else doesn't have a big wave, then they're going to interact differently. So they have to have synchronized water. So the water has to be deterministic. It's determined from like a single value that's being updated from the server. So how are they doing that? They're doing that with, the water is generated with math that's like really deterministic. And that math is an inverse fast Fourier transform. Fast Fourier transforms are really cool math, really complex math that we don't have to talk about here. But the point is, they're using Gerstner waves fundamentally, and Gerstner waves are this pattern of this. All of their water is these different waves layered on top of each other that are just that. And this is a cycloid mathematically. It's a parametric equation called a cycloid. And we'll actually literally just translate that math straight over. Other than that, they're not doing that much special stuff. They're just generating a million Gerstner waves and layering them on top of each other using an inverse fast Fourier transform. So let's look at Gerstner waves. Here's Desmos. Here's parametric equations, right? So here's x of t, y of t. black line, right? As t increases, x increases and y increases. Here's another parametric equation where x is t plus 5 and y is t. So it just does this. Here is a sine wave, the green one. The green one is, the x value is just time. So t equals x, just x. And then sine of t plus a constant is the y value. So the function y shifts left and right based on, you know, because it's like sine of x, right? Like, except we're saying x plus a constant, kind of. It's like the same as, it's the same as that. Same exact thing, but except we have control of the x value. So here's what we can do. Here's what we can do. We can create a Gerstner wave. Here's a Gerstner wave. Cosine of t plus t, sine of t. So imagine like a cosine wave real quick to get the intuition behind this. Cosine of x, right? Here's a cosine wave. Here's a sine wave of x. Okay, so what if I said that, hey, the sine wave's points, let's push them to the right based on the cosine wave's height. That's what we're doing. We're saying push the points to the, push the points based on the cosine wave. So where the cosine wave is 0, relative, you guys are going off about capybaras and I'm not sure you're paying attention. I know math is not very interesting and that's a-okay, I get it, but this stuff is cool and it's like the only math you need. So sine wave here, peak of the sine wave, not pushing the points left or right at all because the cosine wave is 0. But when the cosine wave is at 1, we take this point and we push it 1 unit to the right when the cosine wave is at 1. And this is our Gerstner wave right here, this purple line. So you can see how that works. We're just saying, hey, take our x values and push them by cosine of t. And our y values are just sine of t by default. Just great. Brilliant. That's a Gerstner wave. We can add some parameters to that to give us more control. So here's a Gerstner wave with parameters. It's just a bunch of parameters that can define the choppiness of the water, the chop direction of the water, chop angle. We can define the sharpness, this is like the chop factor. We can define the frequency of the water, etc., etc. Yeah, so Gerstner waves. In Unreal Engine, let's do some Gerstner waves. Here's a Gerstner wave. It's possible to superimpose Gerstner waves on sine waves or vice versa. Water does not travel in sine waves. If you try to put a sine wave on your ocean surface, it'll look really silly. It'll look like this like rolling kind of tube, you know? It's not, Gerstner waves are how water travels. And what we're effectively doing is we're taking a sine wave and like a cosine wave and doing some math to push the points of the sine wave in based on the cosine wave for the same x value, or time value really. So here's time. We're dividing time by the speed, so that, because time is this value that's constantly increasing. It's going 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., etc. And we're dividing it by a speed value. So if I say the speed is like 20, then time gets divided by 20, and it goes 0, 0.2, 0.4, 0.6, 0.8. An absolute world position, dividing it by size to change the scale of the wave. Cool. I add time to absolute world position. So what we're doing is we're shifting this like vector field constantly in all 3 axes on the x, y, and z axis constantly in the world. And we're going to just grab only the red axis. So just imagine this giant vector field that goes from 0 to 1 on like red, except it's not going from 0 to 1, and it's going from like negative infinity to positive infinity. And we're adding time to it. So every point on it is getting time added to it. So every x value is constantly, you know, it's like there's a million x values in our world, and they're just constantly moving to the right because we're adding time to them constantly. So it's just all these x values. Okay, great. Then we're going to take that, and we're going to take the sine of it, and we're going to take the cosine of it. And we're going to multiply the cosine of it by 1, 0, 0, because we're taking the cosine and we're multiplying it by the x direction, x, y, z. So we're saying, hey, take the cosine of that and apply it to this 3 vector. So the output of this multiply is going to be -1, 1, -1, 1. But y and z are going to be 0 and 0. And then the output of this is going to be 0, 0, 1, -1, 1, -1, 1, -1. It's going to be this sine wave, but this sine wave's on like this for the z-axis. So this we've got this vector field of z-axis like sine waves, and this vector field of x cosine waves. Great. All we'd have to do now is add these together. And what we've done is we've effectively said, take every point on our surface and displace it based on this giant like vector field of the x, y, z vector that we're summing up here. As displacement strength, we just multiply it by a displacement strength value, and just like that, we are pretty much done. We can just output that into world position offset and world displacement. And now we have waves. These are big Gerstner waves that are traveling in our world. Look at that. Gerstner waves. Cool. They're really subtle, but they work. And yeah, that's a water shader, you guys. So cool, right? Pretty sick. This is how shaders work. You guys were curious about my grass, I'd imagine. So we can go over how I did this grass if you'd like. We have like another 12 minutes. I can definitely talk about it. Yeah, it is just a 2D plane. Yeah. Yeah, let's look at this grass in wireframe mode. You can see in wireframe mode, it's a bunch of 2D planes. And they render pretty far out, and there's quite a bit of overlap here, which is kind of unhealthy for the engine. Does that mean that the collisions are the same as if the water were a 2D plane? Yes! Yeah, that's a great point. That is a great point. Yeah. So in that example, right, in the water example here, the collision does not follow the shader. Very good. Yeah, collisions don't obey the shader at all. In fact, like, you know, collisions probably wouldn't even be on for this water. If you wanted to create like a water that's actually like you can swim in it, you would probably try to sample the same time value and run the same Gerstner wave equation and use that to obtain the water surface at a specific point. So you would be sampling the same math used to deform the water surface in like a boat, and you'd be like, okay, yeah, it's intersecting here. The way that like boats are done is you know, they've got this like crazy surface that's got a bunch of layered Gerstner waves together, and the surface is doing like woo, woo, woo. The boat, which the boat might look like that. The boat in the game engine has a bunch of just like nodes on it, like maybe one here and like one on the left and one on the right. And each of these, every frame is going, hey, let me run the water equation. And it runs the water equation and it goes, oh yeah, the water is right here. Am I above the water? Yes. Apply no force. Apply just gravity. Am I below the water? How below the water am I? Oh, I'm that much below the water? Apply this much buoyancy force. So like this red sphere right here that's like partially below the water might be like, oh yo, upwards force. And this guy might be like, oh, just no force, just gravity. And that's how like boats are done in games. More often than not. That's probably how Sea of Thieves is doing it behind the scenes. Does the boat have a mask to get rid of the water in the bottom? Yeah, and then so, yep, good points, Thad, good points. So the water's probably intersecting here. And if you're standing in the boat and you're looking down into the boat, there's like water clipping through your boat. You can see these like peaks of water going through the boat. So how are you going to deal with that? Well, you'd probably be like, hey, once the camera is under the plane, nothing will be shown, right? Yeah, right. William's got a good point. Yeah, if you were under the water, you would see nothing. You'd have to like look up, and you would see nothing. You can make the water shade two-sided, but it probably wouldn't look right. So you got to do more magic that says like, hey, on the back faces look different, and you can tell a material to render differently on the back sides of objects. Yeah. Back to this. Sorry. So how would you mask out the water here? You could feed the water the positions of the boat and draw like a circle around the position where the water won't display. You could do distance fields where the in Unreal Engine you can check a box that says generate mesh distance fields, and every mesh will generate a blob around it, and then another blob around it, and like another blob around it, and these fields describe the distance from that field to the nearest point on the surface. From this field to the nearest point on the surface. And there's one at like 0.5 centimeters away, and there's like another one at like 1 centimeter away, and like 2 centimeters away. It's just a series of meshes that say, hi, we are equally distant to the nearest points on the surface of the mesh. And you can reference those inside of materials. You can say, what is the distance to the nearest surface? And you can say, if the surface of the water, if the pixel that I'm looking at is close to the nearest surface is like the boat, then make it completely translucent or something. But then it'll look weird on the edges of your boat. That's a complex question, Thad. One that I've thought about, but not dealt with before. And I would recommend you look it up. But those are just some things off the top of my head, like trying to think of how you could access like the position data for where the boat is and subtract the water's opacity in specifically that region. I don't know any games that do that like really nicely. Like it's just a hard effect to do. A lot of games just try to hide it, but there's a lot of different techniques. Whether distance fields, whether doing something with the camera that's like, hey, if the camera sees the boat, then it shouldn't see the water. You know, like if you're looking at the boat, then don't see the water. So that, like the boat has like X-ray vision through the water, but then that looks weird on the outsides of the water. So you gotta like deal with that a little bit, but that's easier to deal with than like isolating the if water in boat don't. Yeah, it's one line of code, like what Julian just said. Yeah. Let me cover my grass real quick before we end this. We got like 6 minutes left technically on the timeline here. So the grass. How did I approach this? Okay. I began by saying, hey, metallic and roughness. Let's expose these parameters. Great, done. Then I went over here to tangent space normal. There's a setting in the material, tangent space normal. What this is saying is, should this normal output be with respect to the angle of the surface? So what does that mean? Here's a 3D model in Blender. Let me just drag Blender across. God, my mouse is so janked. I've already ordered another one and it's on the way. Here's Blender. Tangent space normals would say, if I plugged into that output 001, it would be like, okay, sure, all surfaces get their normal 001. That's the normal of that surface. That's the normal of that surface. Yada yada yada. It would all be. Nope, I have a G703 one. That would be like what tangent space normals are. But if you uncheck that box and you plug in 001, the normals are understood in world space. So instead of calculating the normals relative to the tangent space of the surface of the object, it would calculate the normals in world space. So like this arrow would get rotated. You know, this arrow would actually be like that. Like the normal of that surface would be up, and the normal of this one would be up, and the normal of the top one would be up, and even the normal of the bottom one would be set to up if I plug in z equals 001, which is exactly what I've done. That is exactly what I've done. So what this is saying is it's saying, hey, all of the grass should be lit as if it's pointing straight up. If I don't do that, then the grass gets really uneven lighting because it's trying to understand where the light is coming from. And it looks hideous. It looks really, really bad if I check tangent space normal. Take a look. Okay, nothing. Oh, okay. Frick, 1 second. I'm confident about this, and I think it's just not recompiling shaders. Just can barely see my screen. It's so bright outside, and I'm using my bad monitor. Come on, come on, come on, window. There you go. There you go. Okay. I'm not seeing the effect of that. I think it's because of subsurface scattering. Let me just go over to... We should be seeing that effect really potently, but we're not, which is really surprising to me. If I crank up the directional light, however, we should see that a little bit better. Let me just do that. 10. Nope. Nope. Even the bright sunlight has not really done that for us. That's interesting. I swear that that does what it does. Did I? What? It's unchecked. I literally. There it goes. Do you guys see that? You saw me check it, right? I'm gonna watch the video replay. I don't believe that. Oh my god, weird. Okay, cool. Cool. Here we go. Come on. Come on, grass. There we go. There's our ugly ass grass. Right. So you see how some of it is deep green and some of it is bright because it's taking into account the angle that each plane is facing relative to the sun, and it's attempting to illuminate it that way, when instead the grass should really behave kind of like this blanket surface that's kind of just pointing straight up. And that's what we wanted to do. We wanted to be really evenly lit by the sunlight or the moonlight or whatever, by pretending that it's all pointing straight up. And so by turning off tangent space and defining the normal for every point on its surface to just be straight up, that's what we're doing. And it gets this really even shading. Brilliant. Then subsurface color. Subsurface lighting. Let's look at what subsurface scattering looks like. Let me just go over here to grass plane 2. These are 3 instances that I've made from it. Let me set the subsurface multiplier to 0. And let me just, what this is effectively doing is it's turning off subsurface for all of the grass. 0 and also 0. There's 3 different types of grass like in the world being spawned. There we go. So that's subsurface lighting off. Now you don't really see the effects of that. It's not very obvious, but if I put this back down to 0.5 and we go near one of the lamps over here, the effect becomes more apparent. Look at that. That's not very smooth. That lighting is not very smooth. Watch what happens as I crank up subsurface. Oh my god, my mouse. As I crank up subsurface. Let me just make this real time. Oh, it is real time. Subsurface 0, subsurface 1. Subsurface 0, subsurface 1. Just focus on the ones that are changing. The ones that are changing are choosing to possibly get more flattened with a player to move around it and step on it. Not easy to do, Andrew. Lots of solutions. I'll discuss like one of them. And in fact, I can implement that for you guys as we talk here if you want to stick around. But if you don't, because it's 6. It is 6, you guys. God, I got to do a lab, and I have a friend coming over at 7. So, yeah. So subsurface rendering, subsurface scattering is pretending that the light is passing through the grass and scattering inside of the grass blade and then coming back out. Ceramics do this. Your skin does this. If you ever point your phone flashlight through your skin and it glows red, that's subsurface scattering. The effect occurs in screen space, which lends itself to a very funny acronym, screen space subsurface scattering, or SSSS for short. I've unironically seen that acronym before. But turning this on gives our grass this really pretty fuzzy shading, and it is computationally not too expensive. So you can see as I turn it on for all the different variations of grass, it now looks, oh, this really nice, gentle fade out of the shading, where the grass is just kind of illuminated by our light. Very nice. Very nice. Cool. What else am I doing with the grass? Well, back here. So that's subsurface color. Now, what is this multiplying by? This subsurface multiplier is just, 0 to like 4 value, because subsurface can go above 1. That's saying, hey, take the color of the grass. This is the final like color of the grass here, as you can see. This is a gradient that's applied to it that gives it a shadow towards the bottom. So let's look at the grass from the side. Oh, right. There's the grass from the side. This right here is a gradient. Here's texture coordinates, right? Here is exclusively the green channel of the texture coordinates. Why is it red? Because when we mask out just the green channel, it becomes like one component of a otherwise three-dimensional vector. So it's just displayed as red because it's the first component, RGB, XYZ. So we're grabbing the green here and we're just treating it as like red. And it's this gradient from top to bottom of black to red. I do 1 minus the gradient and it flips the gradient, right? Because 1 minus 0 is 1, 1 minus 1 is 0. And then I pass that through this cheap contrast node, which is a material function call that looks like this. And it's just it's a quick way to generate contrast in something. I'm not going to go into the math behind it. It's really simple. And you put in something and you give it a contrast value and it generates contrast on this gradient. And the output of that looks like this. And then I can multiply this by this ambient occlusion multiplier parameter, which I have exposed on all of my grass. And I take this and I multiply this value, which is like a 0 to 1 value, or a 0 to whatever the multiplier is set to value, with the color. And what that does is it makes the color really dark at the bottom and brighter at the top. And I get this nice, smooth effect that says, hey, the grass blades at the top should be bright and the grass blades at the bottom should be dark. Normally, this would be handled by the engine. It would go, hey, screen space ambient occlusion. Let me just put some occlusion where the grass base is. But we want to be more computationally efficient. So I've disabled shadows for the grass. This grass is not generating any shadows. There's no like, oh no, the grass blade is big and therefore there should be a shadow at its base from the grass blade that's next to it. That is computationally very inefficient. So instead, we are faking this ambient occlusion effect by just generating a gradient that says from the base of the grass to the top, look dark to bright. Great, amazing. What else do I do? I use this simple grass wind node. This node is kind of fat. It's a material function call. All this is a couple of sine waves, you guys. That's all it is. It's a couple of sine waves with a couple of like really unnecessary math here that it's just sine waves. I could have replaced this with just a sine wave. All it's doing is it's making the grass wiggle for me. It's doing this this wiggling effect right here. There. See a wiggle? Wiggle, wiggle, wiggle. That's what it's doing. It's a big 3D vector field that is positioned in world space, not in the texture coordinate space, so that all of the grass blades that read from it relative to world position. So as those waves travel across the world, they ripple through the grass like sequentially. So there's like a wave here, and it just kind of passes through all the grass. And see, they do this like circle. They're kind of doing that dance that Snoop Dogg does in like the smoke weed every day video, like the with his like hand. You know what I'm talking about? You guys know what I'm talking about, right? Hold on. /tenor Snoop Dogg. This right here. This is the grass is doing exactly what his hand is doing. 1 to 1. It's the resemblance is uncanny. Look at it. It's going left circle, right circle, left circle, right circle. And it's doing this in a wave pattern. Very, very simple. Very simple. So if you want Snoop Dogg grass, that's how you do it. Simple grass wind node. Very convenient. And it's reading these different parameters like wind intensity and wind speed. And it is plugged into the world position offset. However, wind is not alone, right? There's actually more features to this grass. You'll notice that it's in patches. There's these tall patches, and these patches where the grass gets shorter and taller and shorter. And just like in real life, patches where the grass is tall are like, it's like where the grass is well watered, you know? And then these like low patches, the grass is definitely like getting less water. So it's like this kind of paler color. So how am I generating these patches? How am I generating this big pattern that you can see here? I mean, you can kind of, oh God, my mouse. Oh, you can see this pattern here. Look at that. That wasn't me. My mouse clicked 1, 2, 3, 4 times when I just pushed it down. You can see these patches. There's a patch there. There's a patch there, and a patch there. The way these patches are being generated is with a single noise node. Oh, see you, Thad. Need to go anyway. Have fun with the rest of the lecture, guys. Oh, okay, cool. I'm almost done here anyways. I'm just gonna, we've got this world position. We divide it. Again, that's just to adjust the like scale of a texture. See you, Thad. The noise, and try right, goodbye. The noise here that's being generated from it is a noise node. It's a node that's available to you. This is a very expensive node. Oh, you're staying. Okay, cool. Noise is very expensive. It's generated, I think, once at the beginning. I'm using gradient noise, which is pretty cool. It's Perlin noise, pretty much. And it generates this pattern here. And there's a couple of settings to it that you can tweak. I won't go into their details. And then I'm doing 1 minus x to invert the pattern so that like just what's black and what's white pretty much. Giving it contrast with this clump contrast. We can see what the parameter does in a second. And then limiting it from a 0 to 1 value because it's not at a 0 to 1 value. And then this clumping I can take and I can say, hey, here's a texture coordinate. Here's the green mask again, same exact technique, just grabbing this gradient. And I'm saying 1 minus x again, same exact technique, inverting the gradient so we can select the top of the grass and not the root of the grass, right? 1, 0, smooth gradient from 1 to 0, from the top of the grass to the root of the grass. And I'm saying, hey, stretch the grass in the z direction based on the clumping times this gradient. So I'm saying, hey, the grass, stretch it in the z direction. Oh, this is supposed to be a power node, not a multiply node. I just realized. That's funny. That's really funny. Let me make this pow real quick. And exponent. There we go. That might mess up a couple of things, but probably won't. We'll see that effect in a second. The reason I want that to be a power node is because it just gives us more contrast. Like you raise something to a power that values that are like 0 to 1, which these values are by default. You know, they become significantly more intense, and values close to 0 become closer to 0, and you get really like a lot of contrast around 0 and 1, or around 1, and then everything above 1 like shoots up, and everything below 1 shoots down. So this is like contrast. Multiplying it by this gradient so that only the top of the grass gets stretched and not the bottom. And then I'm plugging that into the grass wind as just like a, you know, just the additional world position offset. Wind adds itself to this, and that's the output for world position. So let's see that in action. There's the grass with the exponent effect. You can see it's absolutely janked, right? Let's fix that real quick. Bye, Lay. Let me fix the jank grass. Grass plane. Grass plane 2. Clump height exponent 1. Okay. Save. Clump height exponent 1. I was multiplying it by 5, which is like equivalent to a pretty small exponent. There we go. Okay. So there's our grass again. You can see the height contrast is no longer defined as much. If, however, I go over here and I multiply it by 50, which is equivalent to what I was doing because I was doing 5 times 10, you can see the clumps are coming back. So I can just multiply it by 50 and multiply u by 50 instead of 10. There we go, 50. Save. 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 Bam. We're back to where we were. But now with this exponent, I can control the sort of contrast in the grass and do some really tall grass and some really not tall grass. You can see the effect that that gives. I can really easily control how contrasted my grass height is, and it crushes the low values and accentuates the high values. Very nice. Can also play with the multiplier, but I'll keep the multiplier at 50 and the exponent at 1 for now because that's exactly where it pretty much was. And I'll X those out. What else? So we've covered what okay. We covered what this ambient occlusion gradient does. It's that fake shading. This is height clumping. It's just a couple parameters that say how much are you going to stretch the grass in the Z direction based on the clump data. Based on the clump data, we also switch between different colors. Now, I have a global parameter for grass color, and I have a local parameter for grass color. You can create something called a material parameter collection, which is this right here. And this object has like a bunch of material parameters that I can access anywhere. Grass color 1, grass color 2, grass root color. And I can keep these globally so that a number of different material instances can very easily access them. And then inside of the grass, what I've done is I've set it up so that the user can just check this switch that says use material parameter collection. And if they check it and it's true, it uses this color. But if it's false, then it uses the local color. True, global color, false, local color. So that's all this is. And then it says, hey, switch between these two colors based on the clumping, but with additional contrast if we want it. And then switch between, either use the texture color or not, because it's possible that someone gives me grass that actually has a texture on it, like flowers. And we don't want to replace the flower color with green. We want to keep that pink color from the texture. So if that's true, the user can just check this and it'll switch to the texture color. But if it's false, it keeps passing through the color and it switches between this color and the root color. And the root color is either a local value or a global value. Why is it convenient to keep this as a global value? Because the root color is consistent with the color of the landscape. So across a level, I want the grass to blend nicely with the landscape. So that's what I do there, is I try to keep it like blended with the landscape. And that's what that is. It's this global color. Thank you, Catherine. Take care. Oh, she left just as I was saying bye. And then finally, grass fading. This is saying, hey, get the distance between the camera and the position of the grass. And then it's saying, find a starting position to fade the grass at, subtract how far away we are from it, divide this by transition distance. So this is creating an equation that looks like a slope, a line with an intercept at end fade, an x-intercept at end fade, and a slope that vaguely is like this over 1, I think, or 1 over... rise over run 1 over this. The slope is 1 over this. And we're clamping that from a value of 0 to 1. So on Desmos, let me just like describe what that kind of looks like. That looks like y equals like where x is our distance to the grass. We're saying start the fading process at 100 minus x over like f is going to be our fade distance, and s is going to be our fade start, and we're clamping this to 0 is less than y is less than 1. And so I can say, hey, start the fade, or end the fade, sorry, end the fade. This is where the fade ends. End the fade at 20 meters. Oh, E1, right? Because that's the natural number E. End the fade at 20 meters and transition the fade over the course of 4 meters. And that's what that's doing. It's saying, hey, go from a value of 1 to 0, starting at 16 meters and ending at 20 meters. And that's what that math here is doing. And what we're doing is we're plugging that into dither temporal AA. Temporal anti-aliasing is the anti-aliasing technique that Unreal Engine uses. Because we're not using a translucent shader to save computational complexity, we're using a masked shader, which does not allow for opacity. It's just a 1 or 0 value for whether there's something there or not. There's no 0.5. There's no like partial translucency like there would be in water. It's just a 0 to 1 value. So the way to get around fading this in and out when you don't have partial translucency is dithering, which says, hey, randomly like take a fraction of the pixels and make them zeros instead of ones. And the random amount of pixels that it picks and does this effect on is determined by this opacity, which is what we're plugging in here. But we're also multiplying it by the alpha of the texture, so that it is only, you know, the only visible parts of the texture are the white parts and the black parts are invisible. And that's it. That's the whole grass shader. I've explained pretty much everything here. So we can see what some of these parameters do if I actually play around with them. So like, for example, if I play around with AO contrast, you can see there's that ambient occlusion contrast value. Looks really bad if I crank it up too much, but I found that a value of negative 0.35 looks about right. Ambient occlusion multiplier, I can crank this up, you know, really like change how much of an effect that's having on my grass, but the default value is fine. Clump contrast, if I crank this up, I can, you can see for some of the grass here, because remember, this is affecting about a third of the grass, unfortunately, just because of the way I have it set up so that there's 3 different grasses that fade out at different distances. And there was a better way to do this, and I will implement it eventually, where you use children instances, child instances, where they like keep some of their parameters synchronized across material instances. But I'm not doing that here. But and cluster noise size. So if I change the noise size, I'm going to effectively change the, you see what's, I don't know if you can kind of see that effect there, but for some of my grass, specifically the grass that fades out closest to us, I'm changing like the pattern of the noise texture, but it's 1000, I think is what it's set to. There we go. And now it's the same clusters as the rest of the grass because they all read from the same noise texture. What else? Clump color contrast. If I crank this up, the color gets a severe contrast at the edge of the clump. And you can see that on this grass blade here. It is halfway through the clump. Crazy. Reset that to whatever it was at, 0.1. Metallicity. I can play with how metallic our grass is. Ooh. Yeah. Grass isn't metallic. Go figure. Roughness. A little bit of shininess to the grass goes a long way. It helps with some of the effect here a little bit. Use material parameters. If I turn this off, I get access in the material to our own grass colors. Oh my god, my mouse, please. Okay. See, I have these 3 colors here that I can use. But if I check this, it's using the global material parameters. So it just reads from that parameter collection that I was talking about earlier. I can change the texture. So if Lay makes a different grass texture, I can plug it in. If I check use texture color, it will use the color of the texture, which is black and white, instead of using my colors. But it will still fade in the root texture to the texture. So what we should end up seeing here is white tips on the top of the grass and black tips, or not black, but green at the bottom, because it's going to read the texture at the top and it's going to read the root color at the bottom of the grass once it finishes recompiling that shader. Any second now. Any year now. And I can also crank up the wind intensity for that grass instance and the wind speed. And specifically these grass blades, once they're done, I'll do a thing. Yeah, God, I've been talking nonstop. I threw a lot at the wall today. I hope a lot stuck. I don't know. I love shaders. This was hectic, I know, but if you want to learn more about these, it's really easy to start and you learn so much from them. It's so great. So, oh, there we go. Oh, what? What just happened? Nothing happened. I don't know what happened. That was weird. The grass is really struggling to read the texture color here, I guess, but I don't know. I'll see you, Andrew. It's a pleasure. Um, uh, yeah, grass, guys, grass. Not like just different parameters. I, I don't have much more to add to this, but that's how shaders work. You just gotta kind of break down what you're making into like what properties define how its color kind of looks and behaves, and it does it. It just does. Yeah, it just works. I'm gonna end the recording here, unless anyone has any questions or anything. I'm looking at muted mics. I haven't seen any. Unfortunately, this doesn't seem to. There we go. At the moment that I unchecked that, it worked. I guess because this is stored as a grayscale texture, it didn't know what to look at for RGB. Here's the wind intensity affecting the grass. I can change the wind speed. So there's some of the grass behaving by that different wind value. But if I uncheck these, it just returns to their default values. So, yeah. Yup. Grass, ladies and gentlemen. Grass. The wonders of grass. I freaking love grass. Grass. So good. Man. There's a lot you can do with shaders. Start small. Make like literally just play with tessellation or something. There's so much that you can do. But yeah, that's how we did our grass. I'm gonna close this and not save anything. Good. God. Please tell me nothing saved. Let me just discard. Discard. Yeah, I had a lot of fun. Bye guys. I have a good night. I'm gonna go speedrun a digital logic lab in like 40 minutes and then play Portal 2 until midnight with a friend. So, au revoir. I'll end this recording. Bye.